Hello viewers, in today's session we are going to discuss another important application of Lagrange's mean value theorem. And in this session we are going to discuss a very important inequality in real analysis, right? And here we have to show that e raised to x minus 1 divided by x is greater than 1 but less than e raised to x for all x greater than 0, where x belongs to the set of real numbers. So we'll show or we'll prove this inequality using the concept of Lagrange's mean value theorem. So before proving this inequality, let us quickly revise the statement of Lagrange's mean value theorem. Now, the Lagrange's mean value theorem says that if we have a function, say y is equal to f of x, which is defined in some domain, and the domain is given by this interval, that is a comma b, and if this function f of x is continuous in the interval, that is the closed interval a comma b, and this function is also derivable or differentiable in the in open interval a comma b, then Lagrange's theorem says that there exists a point c which lies between a and b, such that the derivative of this function at this point, that is f prime of c, is equal to this quotient, that is f of b minus f of a divided by b minus a. So this is the statement of Lagrange's mean value theorem. So we have a function y is equal to f of x, which is defined in some domain a comma b. This function f of x is continuous in the closed interval a comma b, and this function has a finite derivative, or this function is derivable in the open interval a comma b. Then there must exist a point c between a and b, such that the derivative, that is f prime of c, the derivative of f of x at this point c, is equal to f of b minus f of a divided by b minus a. So now the first step in proving this inequality is to construct or frame an appropriate function. So let us take here the function y is equal to f of x, which is x minus e raised to x, and here we'll take the interval that is 0 comma x, where x is greater than 0. So now our function f of x is x minus e raised to x, and the interval a comma b is 0 comma x, where a is 0 and b is x. Right now, see, this x is a polynomial function, right? This is a polynomial function, and e raised to x is our exponential function. So now let us first see these two conditions of Lagrange's mean value theorem. Now see, this is the difference of two continuous functions, because polynomial function is a continuous function for all values of x belonging to the set of real numbers, and exponential function is also a continuous function for all values of x belonging to the set of real numbers, right? So this is the difference of two continuous function, and the difference and the sum of two continuous functions is again a continuous function, right? So here this function f of x is continuous in the interval that is a comma b. So here we have the interval 0 comma x, because x is polynomial function, this is continuous, e raised to x is exponential function, and this is also continuous, and this is the difference of two continuous functions. So f of x is also a continuous function. Now, similarly, we can prove the differentiability of this function f of x. Now, the polynomial function x is differentiable for all values of x belonging to R, and e raised to x is also a differentiable function for all values of x belonging to R, right? So this function f of x is also differentiable or derivable in the interval 0 comma x, right? So our function f of x is equal to x minus e raised to x is continuous and differentiable. So f of x satisfies these two conditions of Lagrange's theorem. Hence, there must exist a point C between 0 and x, that is 0 and x, such that f prime of C is equal to this expression, right? So we can now write f prime of C is equal to f of x, because a is 0 and b is x, and here we have f of 0 divided by x minus 0, right? So now let us find out the derivative of f of x. So f prime of x is given by d by dx of x minus e raised to x. So the derivative of x is 1 and the derivative of e raised to x is e raised to x. So here f prime of c can be obtained by replacing x by c. So here we have 1 minus e raised to c, and f of x is x minus e raised to x, and f of 0 can be obtained by replacing x by 0. So here we have 0 minus e raised to 0, and in the denominator we have simply x. So now we can write 1 minus e raised to c, and we have x minus e raised to x minus here we have 0 minus 1, because e raised to 0 is 1. So here we have x, so we can now write x minus e raised to x plus 1. So this minus and this minus, it becomes positive, and here we have x. Now we can transfer the quantities here. So we can rewrite this equation as e raised to c is equal to 1 minus x minus e raised to x plus 1 over x. So we can now write x minus here we have positive e raised to x minus 1 over x. So simplifying this expression by multiplying this 1 by x, and here we have minus x, then plus e raised to x and minus 1. So this x and this x get cancelled, and we are left with e raised to x minus 1 over x. So now we have this equation, that is e raised to c is equal to e raised to x minus 1 over x. So now we have this expression, right? Okay, now let us make use of this inequality. Now this c, it lies between 0 and x. Now what we will do, we'll raise these three terms to the power of e, right? So we can write e raised to 0, and here we have e raised to c, and here we have e raised to x. Now the direction of the inequality remains the same when we raise these three terms to the power of e, because the exponential function is an increasing function, right, for all values of x. So now here e raised to 0 is 1, and here we have e raised to c, and here we have e raised to x. So the purpose of raising these three terms to the power of e is to get e raised to c, and here e raised to c is e raised to x minus 1 over x. So here taking e raised to c as this expression, we can now write 1, and here we have e raised to x minus 1 over x, and here we have e raised to x. So this is our required inequality, that is e raised to x minus 1 over x. It lies between 1 and e raised to x for all x greater than 0, where x belongs to the set of real numbers. So viewers, this is how by the application of Lagrange's mean value theorem, we can prove this important inequality. So now using this inequality, we can make an important deduction using the concept of the properties of definite integrals, right? Now in definite integrals, we know that if we have three functions, say g of x, f of x, and h of x, and these three functions satisfy this inequality, and they are continuous and differentiable in some interval a comma b, right? So if we have three functions satisfying this inequality, then from the properties of definite integrals, we can write integral a to b g of x dx is less than or equal to the integral a to b f of x dx, and this is further less than or equal to the integral a to b h of x dx, right? So now here what we will do, we'll take the functions g of x as 1 and f of x as this one, that is e raised to x minus 1 over x, and h of x as e raised to x, and the limits of integration, we are going to take up this interval, that is 0 to a natural log 2. So now this inequality can now be written as g of x less than f of x and less than h of x. So now if we integrate throughout within these limits, then we can write 0 to natural log of 2 g of x dx, and here the integral from 0 to natural log of 2 f of x dx, and here we have 0 to natural log of 2 and h of x dx. So using this property, right? So here substituting the values of g of x, f of x, and h of x, we have now 0 to natural log of 2, and g of x is 1, and then we have 0 to log of 2, and f of x is e raised to x minus 1 over x dx, and here we have 0 to natural log of 2, and h of x is e raised to x dx. So now let us call this integral as I, right? So we have now integral 1 dx is simply x, and limits are from 0 to log of 2, and here we have I. We are taking this integral as I, and here the integral e raised to x, the integral of e raised to x is e raised to x, and here the limits are from 0 to log of 2. So here we can now write log of 2 minus 0, and this is I, and here we have e raised to log of 2 minus e raised to 0. So this is simply log of 2. Here we have I, and here we have e raised to natural log of 2 is simply 2, and here e raised to 0 is 1, and here we have used this result, that is e raised to natural log of p is equal to p. So now we have 2 minus 1 1, so we have log of 2 I, and here we have 2 minus 1 1, right? So the value of this integral, that is 0 to natural log of 2 e raised to x minus 1 over x dx, it lies between natural log of 2 and 1. So therefore, using this inequality, we have just proved that the value of this integral, that is 0 to natural log of 2 e raised to x minus 1 over x dx, it lies between natural log of 2 and 1, right? And similar type of integral inequalities can also be proved using this inequality.